All right, today we're cracking a classic coding problem. It's one of those that seems simple at first, but it's got this awesome twist. We're talking about LeetCode number 138, copy list with random pointer. This one is a real test of how you think about pointers and memory, so let's just dive right in. So what are we even looking at here? Well, it starts off looking like a totally normal linked list, right? Just a simple chain of nodes. But here's the twist. Each node has this extra random pointer. And this little guy can point to any other node in the list, or nowhere at all. It just completely shatters that nice, neat linear order. And honestly, that's the whole heart of the problem. Okay, so what's our goal? We have to create what's called a deep copy. And that means we're not just copying the values inside the nodes. Oh no, we need to build a whole new list from scratch with brand new nodes. And we have to perfectly recreate that entire tangled web of next and random pointers. The end result? A perfect, independent clone of the original.
And this is where we hit the big wall, the central puzzle, right? Just think about it. You're copying the very first node, you make its clone. Easy enough. But now you have to set its random pointer. What if the original node's random pointer points to, I don't know, the fifth node down the line? Well, you haven't even created the clone of that fifth node yet, so how in the world can you point to something that literally doesn't exist?
Okay, so let's tackle our first approach, which is probably the one that comes to mind first. It's the most intuitive way to solve this. I mean, if you need to remember something you've seen before, what do? You write it down, right? Well, in our case, our notebook is going to be a hash map. This whole solution really breaks down into two main steps, or passes. In the first pass, we just walk through the original list, and all we're doing is creating a clone for every single node and building up our map as we go. You can think of it like we're just creating a manifest. Then in the second pass, we'll use that manifest to connect all those tricky random pointers. So in this first pass, our only job is to create and to map. That's it. For every original node we see, we make its clone, and then we log that relationship in our map. This MAC basically becomes our directory. It tells us, hey, the clone for this original node, it lives over at this address in memory. Simple as that. Okay, now that we've got our map completely filled out, that second pass becomes, well, honestly, it's a piece of cake. We just go back to the original list one more time. If a node's random pointer points to some other original node, we just look up that target node in our map to find its clone, and boom, we connect the pointers. That whole doesn't exist yet problem we had, the map just completely solves it for us. So what's the big takeaway here? This method is super effective, and it's really straightforward. You can explain it, you can code it, it gets the job done. But there's a trade-off, and that's memory. We need extra space for that map, and the bigger our list gets, the bigger that map has to be. That one-to-one growth is what we call O of n space complexity. But what if we could do this without any extra space, right? This is where we get into a much more clever, really optimized approach. It's kind of brilliant, actually. What's so cool about this solution is how it uses the list itself to store the mapping. We don't need a separate map at all. This method is like a three-step dance. It's got a really beautiful logic to it. First, we're going to weave the new nodes right into the original list. Then, we use that woven structure to link up the random pointers. And finally, we separate the two lists back out. Weave, link, separate. All right, let's break down step one, the weaving. We walk the original list A to B to C, right? And for each node, like A, we create its clone, A prime. And we literally tuck it in right behind the original. So now A's next pointer points to its clone, A prime, and A prime's next pointer connects to the original next node, B. We just keep doing this all the way down the line, creating one long, interwoven list. And this is the magic trick right here. Because we did that weaving, we basically have a built-in map. Think about it. If an original node, let's call it cur, has a random pointer to some other nodes, say cur.random, well, we know for a fact that its clone is just cur.random.next in our new woven list. It's always just one step away. So we can set the random pointer for our new node without needing a map at all. It's absolutely genius. Okay, so finally, once all the pointers are set correctly on our new nodes, we do one last pass to untangle everything. We have to carefully reset all the next pointers to separate our new copy from the original. When we're done, both the original list and our new deep copy are left perfectly intact, just like they should be. So what's the verdict on this method? I mean, It's ingenious, right? We get the same ON runtime, but we get O1, that's constant space complexity. That means it doesn't matter how huge the list gets, our memory usage stays the same. It's incredibly lightweight. The trade-off, of course, is that the logic is more complex. The pointer manipulation is definitely a lot trickier to get great. So there you have it, two fantastic solutions to the exact same problem. One is super simple and clear, the other is incredibly space efficient and, well, clever. Let's put them right next to each other to really understand when you might pick one over the other. So the hash map method, it's all about simplicity and clarity. It's easy to explain, it's easier to code, but it's going to cost you memory. The weaving method, on the other hand, is just a masterclass in efficiency. It saves all that space by being way more intricate with its pointer logic. It's really a perfect example of optimizing for a specific constraint, in this case, memory. And this problem just brilliantly illustrates a fundamental truth in software engineering. There's almost never a single best answer. It's pretty much always about trade-offs. What do you prioritize? Do you want memory efficiency above all else? Or do you want code that's simpler to write, easier to read, and less of a headache to debug? And that brings us to the final thought I want to leave you with. Imagine you're in a high-pressure situation, like a coding interview. Which path would you take? Would you go with a safe, clear hash map solution to make sure you get a working answer on the board? Or would you try for the clever, optimized weaving trick to really show off your skills? The answer, and more importantly, how you justify that answer, reveals a whole lot about how you